Hey everyone, welcome to this video where we will dive into the Kruskal's algorithm and its role in finding a minimum spanning tree or MST for short. If you have ever wondered how to efficiently connect points in a network, this is the algorithm for you. Let's get started. What is Kruskal's algorithm? Kruskal's algorithm is a greedy algorithm used to solve the MST problem for connected weighted graph. Here's how it works. First, we sort all the edges by their weights in ascending order. Next, we add edges to the MST one by one, ensuring no cycles are formed. We stop once the MST contains v minus 1 edges, where v is the number of vertices in the graph. We also should ensure that the input graph must be a connected graph. Then we will see what is the minimum spanning tree. A minimum spanning tree or MST is a subset of the edges of a graph that connects all the vertices together, does so with the minimum total weight of edges, and most importantly avoids cycle. Think of it as the most cost efficient way to design a network of roads, pipelines or cables. Why Kruskal's algorithm? Kruskal's algorithm has some great advantages. It's simple to understand. It works well with sparse graphs, which are graphs with fewer edges, and it's efficient, especially when graphs are represented as edge list. Let's dive into the problem. Imagine we have 9 vertices and several weighted edges. Using Kruskal's algorithm, our goal is to find the minimum spanning tree that connects all the vertices with the smallest total weight. Steps of Kruskal's algorithm. Sort all the edges by their weight in ascending order. Start picking the smallest edge. If adding it creates a cycle, we skip it. Otherwise, we add it to the MST. Repeat until the MST has exactly v minus 1 edges. This step-by-step process ensures that we get the most efficient solution. First, sort all the edges in the ascending order of their weights. These are the sorted edges. In the part 1, we are going to see first the steps are in the initial steps there is null and there is no edge considered, and we write all the vertices as separate sets. In the first step, we consider the edge 7 and 8, which has the minimum weight, and we find that 7 and 8 doesn't have the same find value, so we can combine. In the second step, we are combining the 7 and 8 in the first step, and in the second step we are considering the edge 5 6, which is greater than the weight of the edge 7 and 8. Then we find that also the find value of 5 and 6 is not the same, so we are combining 5 6. In step 3, we are considering the edge 1 4, and the find value of 1 4 is not same, right? So we are joining 1 4. Repeating the steps and see the steps 7. In that, we are considering the edge 5 7, but in the previous step we are checking if the find value of 5 and 7 is same or different. See in the step 6, the 5 and 7 are in the same set, which means the find value of 5 and 7 are same. Then we are not including this edge 5 and 5 7. If we include this edge will create a cycle, so we skip it. And in the final step 9, all the vertices are in the same find value, so we don't have to proceed until all the edges are processed. When all the edges are in the same set value, we will stop and consider only the edges that we have written for the connected components. And the final minimum spanning tree is this. I hope you liked the video. Thank you for watching.